Hello there, and welcome to Sleepwalk Space. I'm really glad you found your way here tonight. Maybe you're already settled in, wrapped in something warm, or perhaps you're just taking a few calm minutes at the end of a long day. Maybe your space is dark or softly lit, just enough to see the familiar shapes around you. Maybe there's a window nearby letting in cool air. Whatever your situation, this space is for you. A place where you don't need to be anywhere else. A pocket of quiet where science can unfold slowly, gently. This isn't a test or a lecture. Just ideas, patient ones, that don't require you to hold on to every word. You're welcome to drift, to fall asleep halfway through, to wake up with only pieces remembered and still feel like something settled in. That's exactly the point. Sometimes the most interesting thoughts arrive when we're too relaxed to overthink them. Tonight, I want to talk about something that seems impossible at first glance. A paradox that has puzzled thinkers for generations. The idea that something could stretch on forever and yet still have boundaries, that the universe might be both infinite and finite at the same time. These two concepts seem to contradict each other completely. How could something go on without end and still have limits? Doesn't infinite mean endless, boundless, without any kind of edge or wall? It feels like asking whether a circle can have corners, or whether silence can make noise. The question seems to answer itself, and yet here we are, asking it anyway, because this is what humans do. We ask questions that seem impossible, especially when the world is quiet enough to let them surface. So we'll sit with it together tonight. We'll turn it over, not to force an answer, but to understand what the question really means, to explore what we even mean when we use words like infinite or edge or universe. Sometimes just understanding the shape of a question matters more than finding the answer. But before we drift too far into all of that, let me ask you something simple. How are you feeling right now? Not because I need to know, but because it's worth noticing. You're in a specific moment, a tiny slice of time that will never repeat exactly this way. Right now, as you listen to this, the rest of the universe continues doing what it does. Stars collapse, planets orbit, light crosses vast distances. But this moment, your moment, belongs only to you. That's quietly remarkable. If you're already feeling relaxed or curious or maybe barely awake, I'd appreciate it if you gave this video a gentle like. Maybe subscribe if quiet science conversations are something you want more of. I always enjoy hearing where people are listening from. A quiet apartment, a house in the suburbs, somewhere with rain outside, or just a comfortable bed with soft pillows. If you want to share that in the comments, I'd be grateful. It's like watching small lights appear across the world, a reminder that we're all connected to this vast universe in our own small ways. And, as always, this video is meant for relaxation and curiosity. It's not medical advice, and it won't cure insomnia by itself. But maybe it can give your mind something gentle to follow, something to wander through while your body settles down. That's my hope anyway. So let's begin slowly. No rush, just thoughts. You're there, maybe looking at shadows on the ceiling, or just feeling the weight of your head on the pillow. And maybe you've wondered, like so many people have, what's really out there? Not just beyond your walls or your city, but the real out there. The kind that exists past the atmosphere, beyond the solar system, outside of everything we can touch. The kind of beyond where we point our telescopes and never quite find the end. Maybe you've heard someone say the universe has an edge, and you pictured it like the edge of a cliff or the border of a country. A place where things just stop, where space ends and there's nothing beyond it. Maybe you imagined a spacecraft reaching that edge, hovering at the boundary, unsure whether to turn back. And then, someone says the universe is infinite, and that picture dissolves completely. Infinite means no edge, right? No stopping point, no final star, just endlessness. And yet the thought of infinity is equally strange. It's not something we encounter in daily life. You can imagine something large, incredibly large, larger than all the grains of sand on Earth, larger than the number of stars we can see. But infinity isn't large. It's not a size at all. It's a concept, a direction without destination, a road that never ends. So how can both ideas be true? How can the universe be infinite and still have an edge? The truth is, nobody knows for certain, not yet. But we've developed ways to think about it, to model it, to explore what might be possible. Some approaches are mathematical, others philosophical. Some come from observations, from real measurements gathered by satellites and telescopes. Some are theories we're still testing, still trying to understand. But they all circle the same mystery. What is the shape of the universe? And what does that shape tell us about where it ends, or if it ends at all? When we ask about the edge of the universe, we need to be careful about what we mean. Do we mean the edge of space itself, the farthest point you could reach if you kept traveling? Or do we mean the edge of time, the beginning or end of everything? Or are we asking something simpler, whether there's a place where matter and energy just stop, where you reach the absolute end and can't go any farther? That's where we'll wander tonight. Slowly, one thought at a time. We'll talk about shapes and dimensions. We'll talk about the way space curves, the way the universe expands, the meaning of what we can observe versus what exists. We'll talk about how our perspective as small, temporary beings influences the questions we ask. We'll imagine walking in a straight line, forever. We'll ask what happens if you never turn, never stop, never run out of ground to cover. Do you return to where you started? Do you find a barrier? Or do you just keep going, always forward, never reaching anything final, but not all at once? We'll take our time because part of understanding infinity is realizing it doesn't hurry. It doesn't demand quick comprehension. It's patient, like the stars themselves. So wherever you are right now, however your day went, whatever thoughts are still moving through your mind, just let them slow down. You don't need to push them away. Let them become part of the quiet background, like distant music you can barely hear. We'll talk now, softly, about something very, very big. You can start by imagining a simple room. 4 walls, a ceiling, a floor. You can stand in it and touch the edges. You know exactly where it ends. Now imagine removing the walls. Just the floor remains, stretching flat in every direction. You start walking. No obstacles, no curves, just straight ahead. You keep walking and walking and walking. Time doesn't matter. You never tire. You're always moving forward. Eventually you might wonder, will I hit something? Will there be a wall? Or will this floor continue forever? And what if, after an impossible amount of time, you somehow arrive back where you started without ever turning around? What would that mean? That the surface loops back on itself, that space is curved in a way you couldn't see from your position on it, that you've been walking on something with a hidden shape. Now expand that idea. Replace the floor with the universe itself. Replace your footsteps with the motion of light or the drift of galaxies. What is the shape of that space? Is it flat like an endless plane? Is it curved like the surface of a sphere? Is it open, saddle-shaped, negative? Does it wrap around in dimensions we can't picture? We're getting ahead of ourselves, but only slightly. Tonight, we're not looking for final answers. We're just walking, wondering, asking. And as we do, we'll discover that infinity might not be what we thought, and neither is an edge. Let's start with something basic. What does it mean for space to be flat? When cosmologists use that word, they don't mean flat like a table. They mean flat in a geometric sense. In flat space, parallel lines stay parallel forever. The angles of a triangle add up to exactly 180 degrees. Light travels in straight lines unless gravity bends it. This is the kind of geometry we learn in school, the kind that feels intuitive because it matches our everyday experience. But space doesn't have to be flat. On cosmic scales, it can curve in ways that change everything. Imagine again that you're walking across a vast landscape, carefully moving in a perfectly straight line. You never turn, never veer. If space is truly flat and infinite, you'll never return to your starting point. You'll pass through new territory forever, always seeing something different ahead. But if space is curved, something remarkable happens. Even though you're walking straight, you might eventually loop around and come back from the opposite direction. Not because you turned, but because space itself curved beneath you. The most common way to picture this is the surface of a sphere, like Earth. From where you stand, it feels flat. You can walk in any direction. But if you keep going long enough, you'll circle the globe and return home. The surface has no edge, yet it's finite. There's only so much area. You never find a boundary, but you're not walking through infinite space either. Now, here's the tricky part. The real universe isn't a two-dimensional surface wrapped around a three-dimensional ball. The universe has three spatial dimensions that we experience directly: forward and backward, left and right, up and down. If it's curved, it curves in a way that's harder to visualize, a curvature that happens in higher dimensions. Our minds can't easily hold that shape. We can describe it mathematically, write equations, run simulations, but we can't picture it the way we picture a globe. Even so, that curvature is real. It determines how galaxies move apart, how light bends around massive objects, how the early universe evolved after the Big Bang. The shape of space is the stage on which everything happens. We don't usually notice it, because we focus on what's moving on that stage: the stars, the planets, the expanding galaxies. But like the surface of a lake that shapes how ripples travel, space itself influences how everything behaves. So what do we actually know about the shape of space? More than we used to, but still not everything. Astronomers have studied the cosmic microwave background, the faint afterglow from the early universe. It's not light from stars or galaxies. It's older than both. It's the remnant glow from when everything cooled down enough for light to travel freely. Hidden in that glow are tiny patterns, tiny variations that tell us about the universe's geometry. Not directly, not by showing us a picture, but by revealing how those patterns spread across the sky. From those measurements, current evidence suggests the universe is very close to flat. Not perfectly flat, not with absolute certainty, but close enough that if there is any curvature, it's too slight for us to detect right now. That might mean space extends forever in all directions, Or it might mean the curvature is so gentle that the loop, if there is one, is bigger than anything we can observe. And that brings us to something important. We don't see the entire universe. We see the observable universe, the part from which light has had time to reach us since the beginning. Everything beyond that lies outside our view, not because it's hidden deliberately, but because light from those regions hasn't arrived yet. And depending on how space is expanding, it may never arrive. So when we talk about the shape of the universe, we're really talking about the shape of what we can see. Maybe that shape continues forever. Maybe it repeats beyond our horizon. Maybe it changes. We don't know. But if the observable universe appears flat and if space continues in the same way beyond what we can detect, then the whole universe might be flat too, stretching infinitely in all directions. No boundaries, no edges, just endless space. Or we might be looking at a small section of something much larger, like mistaking part of a gentle curve for a straight line, because we can't see the full arc. If that's the case, the universe could still be curved and finite. It might wrap back on itself in ways we can't quite grasp. And this leads to another thought. If the universe is curved and you keep traveling in a straight line and eventually return to where you started, does that mean there's no edge? Does that make it infinite or not? You've circled back, the journey repeated, but you never hit a wall. So in one sense, it's still edgeless, still unbounded, just not infinite in the way we first imagined. The question gets trickier when we try to measure any of this. What does it mean to measure the size of space itself, when space is what defines size? If you're inside the universe, which we are, and you're using space to measure space, it's like trying to measure a ruler with itself. You can compare distances within it. You can chart separations between galaxies. But you can't step outside to look at the whole shape from above. There is no above. The universe includes everything, all locations, all perspectives. There's no external viewpoint, only views from within. That's part of what makes the question so strange. If you're inside something that might be infinite, but might not be, and you can't leave it, how do you figure out what shape it has? You can only look around, collect data, try to piece together the pattern from the inside out. Still, the shape matters. Not because we expect to draw a perfect map, but because the shape tells us how the universe behaves. If it's positively curved like a sphere, light can travel in loops. If it's negatively curved like a saddle, light spreads out faster than expected. If it's flat, light travels straight, at least straight within the universe's own geometry. In everyday life, we don't notice these distinctions. The scales are too enormous. The effects are too subtle. But on cosmic scales, they matter deeply. They determine how the universe evolves, how fast it expands, whether it will expand forever or eventually collapse, whether parallel lines remain parallel or drift apart or converge. And that structure, that shape, is always there. Even when everything seems still, even when galaxies drift apart so slowly we can't perceive the change, even when the night sky looks identical year after year, the shape of space is the foundation. It holds the silence. It frames the stillness. And it might also shape the answer to our central question. Because if space has a shape, whether curved or flat or something stranger, that shape might tell us whether an edge is even possible. So far, there's no evidence of a wall, no sign of a boundary where things simply stop. But there is evidence of geometry, of structure, of rules. And that geometry might be the key to understanding where we are and what it means to move through something that doesn't end, yet makes us wonder where it begins. So what do we mean by edge? It sounds so simple. The edge of a table, the edge of a page, the edge of a cliff. It's where something stops, where one thing ends and another begins, usually nothing or air or empty space. Edges are clean boundaries, defined by contrast. Inside is the object, outside is not. We use edges constantly to orient ourselves. They create structure. They separate what's contained from what isn't. But when we ask whether the universe has an edge, we're not talking about something sitting on a table. We're asking whether all of existence, all of space and time and matter could have a boundary. And if it does, what lies beyond that boundary? And if it doesn't, how do we make sense of that? It's difficult to picture a thing that includes everything, yet still has an outside, because outside implies something additional, something else. But if the universe contains all space, there shouldn't be an outside at all. An edge in that context would be a line beyond which there is what exactly? Not space, not time, not even emptiness, because emptiness is still a form of space. So what then? A kind of non-place, the absence of anywhere to be. That's where the familiar meaning of edge starts breaking down. In a physical sense, an edge only exists in relation to what's on the other side. A book ends where air begins. A sidewalk ends where the street starts. But the universe doesn't sit on anything. It's not placed on top of something else. It is the foundation. It's the space in which other things exist. So when we ask about an edge to the universe, we're really asking one of two things. Either is there a point past which space doesn't continue, a literal outer limit, or is there some fundamental transition, a change in structure or conditions that marks the end of familiar territory and the beginning of something different? That second kind of edge is more subtle. It's not a wall. It's more like a threshold. You might not see it or feel it, but beyond a certain point, the nature of reality could shift. Maybe the physics changes. Maybe space isn't structured the same way. Maybe there are regions with different properties, different particles, even different dimensions. There are theories suggesting such things. Some versions of cosmic inflation, the idea that the universe expanded extremely rapidly right after the Big Bang, propose that our observable universe is just one bubble in a much larger structure. Each bubble might be a separate universe with its own characteristics. In that case, there might be a kind of edge, not a hard wall, but a boundary between bubbles, a region of transition. But we don't have evidence for that yet. And that raises another point. When people hear edge, they often imagine a place you could visit, a location. You reach the end, you look over the side, you see something or nothing, or maybe you fall. But that assumes space works like terrain, a fixed landscape you can cross. In reality, space is dynamic. It expands. It curves. It's not a surface laid out flat. It's part of the system itself, and your movement through it is shaped by its structure. Let's consider a comparison. Imagine a video game world. Not the characters or graphics, but the code defining the environment. Maybe the game world is a giant square. If you walk to the edge, you hit an invisible barrier. That's one kind of edge, the hard limit of the system. Nothing exists beyond it, not even in theory. The developers didn't create it. Or maybe the world wraps around. You walk east and eventually appear back on the west side. That's another kind of edge, a boundary that loops. It's not infinite, but it has no stopping point. You never hit a wall, you just repeat. Or maybe the game world generates new terrain as you explore, creating space dynamically. From inside, it feels infinite, but from outside, from the perspective of the code, it's still limited. It exists only as far as you've traveled. Now bring that back to our universe. We don't know if it's a closed system like the first example, a looping one like the second, or a generating one like the third. But we do know that from our perspective, there's no observed barrier. Light reaches us from billions of light years away. Space continues in all directions, at least as far as we can measure. But even our measurements have limits. The speed of light gives us a horizon, a maximum distance we can observe. Not because there's an edge there, but because light from beyond that distance hasn't had time to reach us yet. We call this the observable universe. It's like being in fog. You can only see so far, but that doesn't mean the world ends at the fog's edge. It just means you can't see past it. Maybe there's more beyond, maybe not. That idea, the observable horizon, is sometimes mistaken for a literal boundary, but it's not. It's just a limit set by time and the speed of light. The universe might extend far beyond it, or it might not. We simply don't know. But here's what often gets overlooked. If the universe does have an edge, it's not something we could ever reach in a conventional sense. Not because it's too far, but because of how space itself behaves. The universe is expanding, not into anything, just expanding. The space between galaxies is stretching. And the farther away something is, the faster it recedes from us. At a certain distance, things move away faster than light. Not because they're breaking physics, but because the space between us and them is expanding so rapidly. That means, even if you could travel at light speed, you'd never catch up. You'd never reach those regions. They're forever beyond reach, past the cosmic horizon. That's another kind of edge. Not a wall, not a place, but a limit on what can ever be known, ever be reached, ever be influenced. And yet that limit changes over time. The observable universe grows as light from more distant places arrives. Our horizon expands. The edge shifts. So when you lie there wondering whether there's an edge to the universe, the answer depends on how you define edge. If you mean a place where space ends, we haven't seen anything like that. If you mean a horizon beyond which we can't see, then yes, but it's not a boundary in the usual sense. If you mean a fundamental change in conditions, a region where the universe transitions into something different, then maybe. But we have no proof yet. Most importantly, the edge isn't fixed. It's not waiting to be found. It's not marked by a warning sign. It's a concept that changes depending on perspective, tools, definitions. It might be more useful to stop thinking of edge as a location and start thinking of it as a relationship between what's known and unknown, between what we can see and what we can't, between what exists for us and what exists beyond us. That's what makes the question rich. It's not about finding a wall. It's about understanding what it means to reach a limit and what lies just past the edge of knowing. And as we continue, we'll turn to one of the most misunderstood ideas of all: infinity. What is it really? How does it differ from merely large? And can something be infinite and still have no edge? Infinity isn't a number. We sometimes use it like one, in conversation, in jokes, in exaggerations. We say something takes forever, that there are infinite possibilities, that the universe is infinitely large. In those moments, the word usually just means a lot, more than we can count, bigger than we can manage. But in science and mathematics, infinity isn't just a bigger number. It's something fundamentally different. It's not part of the counting system. You can't measure it with instruments, or reach it by adding one more and one more and one more again. It's not what you find at the end of a long sequence of zeros. It's what lies beyond the idea of endings altogether. If you take a calculator and enter a number too large for it to handle, you might get an error. But infinity isn't an error. It's a concept, a definition of unboundedness. It's what you describe when you say something never stops, never finishes, never runs out. It's not 10 billion, or a Google, or even a Googleplex. Those are still numbers. They have positions. They can be written down. Infinity never arrives. It's a direction, not a destination. This is why people get confused when scientists say the universe might be infinite. It sounds like it should be measurable. If something is infinite, surely we should be able to talk about how big it is. But infinity doesn't work that way. You don't measure it. You approach it. You describe conditions under which something grows without bound. It's not the thing, it's the behavior. In mathematics, you might see a phrase like as x approaches infinity. That doesn't mean x becomes infinity. It means x grows larger and larger without limit. The process is the point. Infinity is never reached. It's what lies at the end of a pattern with no end. And that's where things feel strange. In the real world, we don't encounter truly infinite things. We have large, we have small, we have fast, we have slow. But we don't have actual infinity. There's nothing you can point to and say this here is infinite. Even the sky, which feels endless, is full of objects we can count. Even the ocean, which seems to stretch forever, has boundaries and depths and limits. So when we talk about the universe being infinite, we're making a statement not about size in the traditional sense, but about structure. We're saying, as far as we can tell, there's no edge, no limit, no sign of stopping. The geometry of space is such that it continues and continues and continues. This doesn't mean the universe contains every possible thing. It doesn't mean somewhere out there every version of reality plays out. It simply means space itself, the fabric of the cosmos, might extend without bound. That you could keep moving in a straight line and never come back around, never hit a wall, never find a final star at the edge of creation. But here's where it gets subtle. Something can be finite and still have no edge. Think again of the surface of a sphere. It has total area. You can calculate it, but there's no boundary, no cliff, no end. You can walk in any direction and never fall off. That's a finite surface with no edge. Now imagine that in more dimensions, a universe that wraps around itself in ways we can't picture. It might be finite in volume, but unbounded in experience. You'd never find a border because there isn't one. You just keep going, around and around, always forward, never stopping. That's different from an infinite universe, but it feels similar. Both are edgeless. Both let you keep going, but one loops, the other doesn't. And that's why the difference between infinite and edge-free matters. You can have one without the other. Just because there's no edge doesn't mean the universe is infinite. And just because the universe is infinite doesn't mean it contains everything imaginable. When scientists try to determine whether the universe is infinite, they look at clues. The curvature of space, the way light behaves, the distribution of galaxies. Based on what we see, the universe appears to be either flat or very close to flat. If it's exactly flat and doesn't loop back, then it probably is infinite. Not because we've measured every region, but because the geometry implies it never folds back. It just keeps going. But remember, our observations are limited. The observable universe is a sphere around us, about 93 billion light-years across. That number can be misleading. The universe is 13.8 billion years old, but because space itself expands, the edge of what we can see is farther than that. Light has been traveling all that time, and the fabric it moved through has stretched. Still, that 93 billion light-year span isn't an edge. It's a horizon, a distance beyond which light hasn't had time to reach us. What lies beyond is unknown, and that unknown space might be part of an infinite whole, or it might be a patch in a larger but finite universe. There's no way to know, at least not yet. Some people struggle with infinity because it feels too abstract, too big. It doesn't behave like things we know. But that's fine. You don't have to visualize it completely. You can just understand it as a kind of openness, a system without walls, a space where there's always more space. That's enough. And it's worth saying infinity doesn't mean chaos. It doesn't mean anything can happen or everything does happen. It just means there's no upper limit on extent. The system could still be ordered, still follow rules, still evolve predictably. Infinity doesn't erase structure. It just removes the fence. In fact, some infinities are bigger than others. That sounds strange, but it's well established in mathematics. The set of counting numbers, 1, 2, 3, and so on, is infinite. So is the set of real numbers between 0 and 1. But there are more real numbers than counting ones, different sizes of infinity, different scales of the unbounded. That kind of thinking helps mathematicians reason about sets and limits. In physics, it's harder to apply because we don't just want to know whether the universe is infinite. We want to know what that means for us, for our position, for our future, for the shape of space and time itself. And this leads to something deeper. If the universe is infinite, then the observable part, the bit we can see and measure, is just a small patch, an island in a vastly larger ocean. And if that ocean continues without end, it raises more questions. Are the physical laws the same everywhere? Is matter distributed evenly? Are there parts of space that look nothing like our own? We don't know, but we can guess. Based on what we see, the universe looks remarkably uniform on large scales. That suggests our patch isn't unique, that the rest of the universe, infinite or not, probably follows the same rules. But again, we can't test that directly, which means that even though infinity might be part of our model, it remains a placeholder, a way of saying we don't see a boundary and nothing in the equations requires one. That doesn't mean there isn't one. It just means we haven't found it. And this, in a way, brings us back to edges. Because if the universe is infinite, then there's no edge by definition. But if it's finite and unbounded, if it loops, then again, there's no edge. So in either case, we're left with a strange conclusion. The universe might have no edge, whether it's infinite or not. That's the part people tend to miss. The absence of an edge doesn't tell you whether space is infinite, and infinity doesn't guarantee the absence of a boundary. It all depends on shape, on structure, on geometry. So maybe it's time to stop asking whether the universe is infinite and start asking something more useful. What's the shape of the space we live in? How does it curve? How does it connect? How does it guide motion, light, time? because those are questions we can begin to answer, not by looking for walls, but by watching how things move, how galaxies drift, how background radiation spreads, how gravity bends light. If you've ever read about space, you've probably heard someone mention a balloon. Not because the universe is made of rubber, but because balloons offer a useful way to picture something otherwise hard to imagine. Not perfect, not literal, but helpful, especially when we talk about space expanding. The balloon comparison usually starts like this. Imagine inflating a balloon. On its surface are tiny dots, maybe drawn with marker. Each dot represents a galaxy. As the balloon inflates, the dots move farther apart. Not because the dots themselves travel along the surface, but because the surface is stretching. There's more space between the dots even though they're not moving across it. This model gives us a way to think about how galaxies in the real universe move apart as space expands, not because they're flying away from each other like debris, but because the space between them is increasing. The galaxies stay roughly where they are. The distance grows. Now here's the important part. The balloon surface represents space, not the air inside, not the balloon as a whole, just the two-dimensional surface. That surface has no edge. You can move across it in any direction, keep going, and eventually circle back. It's a finite surface, but it doesn't have a boundary. No edge, no wall, just a smooth, continuous surface that curves around. That's what makes the balloon helpful. It shows how something can be finite and edgeless, how you can move through space without ever finding an end, even though the total area is limited. As the balloon inflates, every point on the surface moves away from every other point. There's no central dot, no origin on the surface. Every location sees the rest of the balloon expanding away from it. That's the first thing people misunderstand about this model. They try to find the center. But the center of the balloon's expansion isn't on the surface at all. It's in a higher dimension, part of the full three-dimensional space in which the two-dimensional surface exists. From within the surface itself, the expansion looks the same everywhere. There's no special spot, no preferred direction. And that's the second mistake. Imagining the expansion is happening into something. When the balloon inflates, its surface grows larger. But from the perspective of a dot living on it, the surface doesn't expand into anything. There's no outside in the two-dimensional world, just more surface, more space between things. Now, take that concept and imagine it with three-dimensional space, our actual universe. The expansion we observe isn't happening into something else. Space itself is stretching. There's more distance between points over time. Galaxies aren't flying apart through the universe. The universe itself is getting bigger. We don't see this on small scales. Your room doesn't expand. Your planet doesn't grow. The solar system doesn't drift apart. Gravity holds those things together. But on larger scales, between galaxies, between clusters, the expansion becomes noticeable. The farther away an object is, the faster it seems to recede. That's not because it's speeding away, but because the fabric of space between us is expanding. So the balloon helps, but it's still just a comparison. The universe isn't the surface of a balloon. It has three spatial dimensions, not two, and there's no evidence of a higher dimensional space surrounding it. If the universe curves, that curvature happens within itself, not into something else. There's no outer air, no room space is growing into. People often ask, if the universe is expanding, what is it expanding into? The answer is it's not expanding into anything. Expansion doesn't require an outside. It just means distances between points increase over time within the system itself. The concept of outside doesn't apply when space contains everything. It helps to think about coordinates. In a normal room, you can describe a location by saying how far it is from the walls. In space, there are no walls. So we use relative positions, how far one thing is from another. When the universe expands, those relative distances increase. The coordinate system stretches, not because anything moves outward, but because the measurement between things changes. That's why the balloon example works best when you think about being on the surface, not inside it. A creature living on that surface would never see an edge, would never reach the middle, would never run out of space to explore. And if the surface kept inflating, they would see other points moving away from them in every direction uniformly. No center, no edge. Now, apply that thinking to the universe. We look around and see galaxies moving away from us. The more distant they are, the faster they recede. But if you were in a different galaxy, you'd see the same thing, everything moving away from you. It's not that our galaxy is special, it's that expansion looks the same everywhere. This is called the cosmological principle, the idea that the universe is uniform on large scales. It looks the same in every direction and from every location. No center, no preferred spot, just vast expanding space where the rules apply everywhere. That might sound abstract, but it has real consequences. It means our observations, the light we see from distant galaxies, the patterns in the cosmic microwave background, aren't just local curiosities. They're windows into how space itself behaves, into the geometry defining expansion. And the geometry, as far as we can tell, is flat or very close to flat. That doesn't mean the universe is like a table. It means that on large scales, light travels in straight lines. Triangles behave as expected. The rules of standard geometry apply. But that doesn't rule out curvature. It just means the curvature, if it exists, is too slight to detect. The balloon surface is positively curved. A saddle is negatively curved. Our universe appears to be somewhere between close enough to flat that we don't see looping or distortion across billions of light years. Still, that doesn't mean the balloon idea is wrong. It's just one possibility. If the universe is positively curved, it might be finite and unbounded like the balloon surface. If it's flat and infinite, the comparison breaks down. There's no looping, no return path, just space continuing in every direction forever. And here's where the comparison becomes really helpful again. Because even if the balloon surface doesn't match our universe exactly, it reminds us that edges aren't necessary. You can have finite space with no edge or infinite space with no boundary. The absence of a wall doesn't tell you which is true. It also reminds us that expansion doesn't require an outside. You don't need a larger container. The container is the space itself, and that space can grow not by adding more stuff, but by stretching the distances within it. So, when you think about the universe expanding, try not to picture a ball getting bigger in a room. Picture it more like the balloon surface, growing from within, in all directions, without needing an outside to grow into. The space itself becomes more spacious, and now we can ask something more specific. If space behaves this way, expanding, stretching, possibly looping, then what does that mean for how it's shaped? Can we classify it, name it, predict how it will behave? Because the next layer of this question isn't just about comparisons. It's about geometry. We've talked about space stretching, about light traveling through expanding fabric, about balloons and infinity, and how the universe might not need an edge at all. But there's a more technical version of this discussion, one that scientists and cosmologists return to again and again when trying to understand how the universe behaves. The question of its geometry, specifically whether space is flat, open, or closed. These aren't just abstract labels. They're real models that describe how the universe might be shaped on the largest scales. And even though we're used to dealing with curves and angles in everyday life, cosmic geometry happens on a completely different scale. It's not the curve of a hill. It's the curve of the universe itself, the way it bends light, sets paths, affects time. Let's start with the one we're most familiar with: flat. When scientists say the universe is flat, they don't mean it's like a sheet of paper stretched across a desk. It's not two-dimensional. It means it follows the rules of standard geometry, the kind we learn in school. Parallel lines stay parallel. A triangle's angles always add up to 180 degrees. Light travels in straight lines unless bent by gravity from a massive object. In a flat universe, space doesn't curve inward or outward on its own. It can still expand, and it does, but the expansion doesn't come with any natural tendency to loop back or spread out into a saddle shape. It's neutral, balanced. Flat space is infinite unless something else limits it. It keeps going in every direction, and the more you zoom out, the more it continues behaving the same way. Next comes the closed universe. This one curves inward like the surface of a sphere. Not just a ball in space, but space itself behaving like the surface of a higher dimensional sphere. This is harder to picture, because we don't live in space that naturally wraps like that. But the key idea is this: in a closed universe, if you travel far enough in a straight line, you eventually return to where you started. You might never notice the curve because it's spread out over billions of light years, but it's there, gently guiding paths into loops. This kind of universe is finite. It has limited total volume, but it has no edge. That might feel strange at first. How can something be finite and still have no boundary? The answer lies in how space connects back to itself, like the surface of a planet. You can travel forever without hitting a wall, because you're always moving within a loop. There's no outer space to fall into. Everything exists inside the structure. A closed universe also implies certain things about its past and future. For one, it would have started with a big bang just like any other model, but it might eventually stop expanding. Gravity, over enough time and distance, could pull everything back in. The universe would stop growing, reverse course, and collapse. That collapse is sometimes called the Big Crunch. It's not the only possibility, but it's one that follows naturally from a positively curved closed model. Then, there's the third option: open. An open universe curves the opposite way, outward like a saddle. It's not closed in on itself. It doesn't loop. In this model, parallel lines diverge. A triangle's angles add up to less than 180 degrees. Light traveling through it tends to spread out more over distance. This kind of space is infinite, like the flat model, but it stretches in a different way. It's unbounded, but it also naturally tends to keep expanding forever. In an open universe, there's no danger of collapse. The expansion might slow, but it never fully stops. Galaxies continue drifting apart. Stars burn out. Matter thins. Over vast time scales, the universe grows colder, emptier, quieter. No big crunch, just a gradual fading into stillness, a slow march toward a state sometimes called heat death. These three models, flat, open, closed, are more than drawings on a whiteboard. They're solutions to Einstein's equations of general relativity. They describe how space behaves under gravity, how mass curves space, how time is influenced by energy, and the shape of the universe isn't chosen randomly. It depends on one crucial thing: density. Not just the density of matter like stars and gas, but the total energy density of the universe, including dark matter, dark energy, radiation, everything. There's a critical threshold. If the universe's actual density is exactly equal to this critical value, space is flat. If the density is higher, space curves inward, a closed universe. If it's lower, it curves outward, an open one. So how do we figure out which it is? We measure. We observe the cosmic microwave background, the faint glow from the early universe, and look at how small fluctuations in that glow are distributed across the sky. The patterns in that light tell us how space bends, not just nearby, but across vast scales. We also look at how galaxies are spread, how distant supernovae fade, how gravity lenses light from behind massive objects. And so far, all this evidence points to a flat universe, or at least a universe that's flat enough that we can't tell the difference. If there's curvature, it's slight, too small to measure with current tools. That doesn't mean the universe is perfectly flat or infinite or destined to expand forever. It just means that right now, from where we are, it looks flat. And yet, flat doesn't mean simple. A flat universe can still expand. It can still accelerate. It can still be filled with structure, with filaments of galaxies stretching across space, with voids where very little exists. It can still change over time, still produce stars and black holes and planets and light. The flatness just describes the backdrop, the geometry. What happens on top of that depends on the contents, and those contents are strange. Dark energy, for example, makes up the majority of the universe's total energy density. We don't know exactly what it is, but we know it's causing the expansion of the universe to accelerate. That acceleration doesn't change the geometry, but it changes the destiny. A flat universe with enough dark energy will expand forever. Not because it's open, but because the outward push overwhelms gravity's pull. In that case, you get a universe that keeps growing colder, emptier, more stretched out. Galaxies move away from each other faster and faster. Eventually, they fade beyond visibility. The night sky dims, stars die out, black holes evaporate over incomprehensible timescales, and what's left is just space, quiet, sparse, still expanding. So when people ask, is the universe flat, open, or closed, the answer for now is flat. But that answer comes with uncertainty, with margins of error, with assumptions about dark energy, about inflation, about measurements. The question itself is part of a larger search, a search for the shape of space, the fate of expansion, the true geometry of everything. But one thing is clear. No matter which model you choose, none of them require an edge. Flat space doesn't stop. Open space doesn't stop. Closed space loops back. But none of them include a boundary, a wall, a place where space just ends. That idea that space has to stop somewhere doesn't appear in the models. Which brings us back to where we started. When we imagine edges, we're thinking in terms of objects, tables, rooms, maps. But the universe isn't an object inside a larger container. It is the container. And whether it's flat, open, or closed, it has no outer side. There's no direction you can travel that takes you to the end. Just space, continuing, curved or not. So perhaps instead of asking whether space has an edge, we should be asking what kind of space we live in, what its rules are, what its geometry implies. Because once we know that, we can understand more clearly what it means to move through space, to observe it, to live in it. And now that we've seen how space might curve inward, outward, or not at all, there's a natural next question to ask. If you can have a space that's finite but still without edges, then how does that work? How can something be boundless and yet not infinite? Earlier, we talked about the surface of a balloon, not as a perfect model of the universe, but as a useful way to think about something important, how space can be finite and still have no edge. That idea sounds contradictory the first time you hear it. How can anything be limited in size and yet not have a boundary? How do you finish something without reaching a stopping point? We're used to thinking in terms of edges, of corners, frames, outlines. We like shapes that have borders. A room has walls, a page has margins, a planet has a surface. Even the ocean, which feels endless when you look out across it, is actually held by the shape of the Earth. But not everything works that way. Mathematically, it's possible for a space to be both finite and unbounded. It doesn't stretch on forever, but there's no location where it stops. You can move through it endlessly without falling off or hitting a wall. And yet, the space you're moving through contains a limited amount of volume. That's what we mean by boundless but finite. And it turns out that kind of space isn't just possible. It might actually describe the shape of our universe. To see how that works, start with a circle, a perfect one drawn on a flat surface. The line itself has a length, a circumference. You can measure it, but it doesn't have an end point. If you start anywhere on the circle and move forward, you'll eventually return to your starting point without ever stopping or changing direction. There's no edge, just the loop. That's a one-dimensional example. Now go one step up. Imagine the surface of a sphere like Earth. Not the whole ball, just the outer shell. That surface is two-dimensional. You can move north, south, east, west, but you're always stuck to the surface. Again, it has finite area, but it has no boundary. You can fly around the Earth as many times as you like, and you'll never find an edge. There isn't one. Now take one more step. A three-dimensional version of this idea. A space that's the three-dimensional equivalent of a sphere's surface. It curves back on itself in every direction, but it's not sitting inside a larger container. It's self-contained, complete. You can travel through it in any direction indefinitely, and eventually return to where you started, just like flying around the globe. That's what a finite, unbounded universe could be. A shape where the total volume is limited. There's only so much space. But there's no outer wall, no final coordinate, no last galaxy, just more space connecting back around. No edge, no beyond. Everything is included. Of course, this isn't something we can visualize directly. Our brains aren't built to picture higher dimensional shapes. We can draw analogies, look at slices, imagine surfaces. But the full shape of a finite, three-dimensional curved space is abstract. That doesn't make it less real, just harder to draw. And in physics, the reality of a shape isn't judged by whether we can picture it. It's judged by whether it explains what we see, the way light bends, the way galaxies spread, the way background radiation patterns appear across the sky. All of that gives us hints about the underlying shape of space, the possibility of a finite but unbounded universe is one of those hints because we don't see a wall. We don't see repeated patterns that would suggest a small closed loop. But we also don't see any evidence that the universe has to go on forever. The math allows for a space that curves gently back on itself, large enough that the loop is too big for us to detect, but still finite in total size. And here's where things get interesting. A boundless but finite universe behaves in many ways like an infinite one. You can travel endlessly in a straight line. You never run out of room. You never see a boundary. From your point of view, space just keeps going. But it doesn't. Not in the strictest sense. It returns. It closes. It connects. If this sounds like it overlaps with the balloon analogy again, it does. The balloon surface is boundless and finite. So is the globe. So is a torus, a donut shape, which you can imagine as a flat rectangle where opposite edges connect. Walk off the right side, you appear on the left. Go off the top, you come back from the bottom. No edge, just connection. Now imagine that kind of connection happening in 3 dimensions. No wall, just continuity of space. That's a topological idea, not just about curvature, but about how space is stitched together. And that stitching doesn't require an outside. It's not folded up in a higher space. It just is the space. This has implications for how we think about travel, about light, about the history of the universe itself. In a boundless but finite universe, a beam of light could in theory circle back around. If the universe was small enough, you might see an image of a galaxy not once, but twice, once directly and once coming from the other side. We've looked for signs like that, repeated structures, mirrored patterns, but so far we haven't found any. That doesn't rule out the idea. It just means that if the universe does loop, it does so on a scale larger than what we can currently observe. The loop might be hundreds of billions of light years across, maybe more. And so, from our perspective, it might as well be infinite. That's the subtle part. Our tools are limited. Our view is small compared to the total structure. What feels boundless to us could still be finite, and what feels endless might eventually reveal a return path, a route through curved space that brings you back home. But you'd never feel it, not the loop, not the edge, not the connection. The journey would take longer than the age of the universe. The loop is real, but unreachable. That's the difference between what's true and what's observable, between what a model allows and what we can ever test. Still, even that possibility changes how we think about edges, because the presence or absence of a boundary isn't tied to size. It's tied to structure, to the way space bends and how it connects with itself. You can build a world that's infinite, new terrain generated as you explore. But you can also build one that loops. Walk far enough, and you're back where you began. From inside, both can feel the same. You never see a wall, you never hit a limit. But one is infinite, the other isn't. So when people say the universe is expanding and ask what it's expanding into, or whether it has an edge, or whether it's infinite, those questions all come back to this: how space behaves when you move through it, whether it loops, whether it curves, whether it connects. And none of that depends on having a wall. You don't need one. Not to be finite, not to be complete, not even to be infinite. You just need a geometry, a structure, a way for space to work. Or if space had an edge, where would it be? You could start the question another way. You could ask, how far do you have to go to reach the end of the universe? What would you find when you got there? Is it a place, a boundary, a limit you can cross? The problem is, the question is built on the way we experience the world around us, where things have containers, and containers have ends. You walk to the edge of a forest. You sail to the edge of a lake. You reach the edge of a city and find open land. But in each of those cases, you're moving from something into something else. You're transitioning from one defined region into another that's either emptier or just different. So it's tempting to ask the same thing about space. But space doesn't sit inside anything larger. It isn't placed on top of a platform. It doesn't exist within a larger arena that holds it in place. As far as we know, space is everything, all positions, all directions, all coordinates. If there's an edge, it wouldn't be like the border of a field or the rim of a cup. It wouldn't be a place you could walk to or fly to or even point at. But let's play with the idea anyway. Suppose we take the fastest traveler we know, a photon, a particle of light, and we launch it in a straight line with nothing to stop it. It moves at the speed of light, never slows down, never looks back. It doesn't get tired, it doesn't wander, it just goes. Where does it go? From our point of view, that photon moves through expanding space. It covers distance, but that distance is changing as it travels. The space between points stretches. So even though it's moving at light speed, the destination it's moving toward is also moving away. Not because it's fleeing, but because space itself is growing. In that kind of universe, the photon might never catch up to certain regions. They're too far, expanding too fast. Even light can't close the gap. So, there are places in the universe that are forever out of reach. Not just for us, but for anything, ever. That's called the cosmic event horizon. It's not a wall. It's a limit, one that's defined by the expansion of space itself. So already we have one kind of edge, a practical one, a boundary on what can be touched or influenced even in principle. But it's not a place. It's not a fixed location. It's a distance that depends on how fast the universe is growing and how long it's been doing it. That distance is currently estimated to be around 16 billion light-years away from us. Past that, anything we do now won't ever affect what happens there. Not in a trillion years, not ever. But again, that's not the edge of space. It's just the edge of interaction. Beyond that horizon, space continues. Galaxies exist. Light travels. Stars burn. But from here, those events are permanently disconnected. They belong to a region of space we'll never reach. If you followed that photon, it wouldn't hit a wall. It wouldn't bounce back. It would just keep going, always moving into new space, never repeating, never circling back unless the universe loops, which we don't currently see evidence for. So where is the edge? If you asked that photon, it wouldn't have an answer. From its point of view, if you could say a photon has a point of view, everything is always here. At light speed, time doesn't pass. Distance doesn't stretch. The entire journey collapses into a single moment. There's no past, no future, no path, just transmission. But for us, watching from slower frames of reference, the photon's path stretches across time. It shows us that space has no obstacle, no ending, just more space. And if we zoom out, not in space but in scale, we start to realize that the edge, if it exists at all, wouldn't look like a feature. It wouldn't be marked. You wouldn't see it ahead growing larger. It wouldn't even reflect light, because there'd be nothing on the other side to illuminate it. It might not even make sense to call it an edge, because edges divide things, one side and the other. But if there's no other side, then what is the edge dividing? It would be the end of space. But beyond that would be not space, not emptiness, just the absence of dimension. And our language doesn't handle that well. We want to say it's nothing, but we imagine nothing as a kind of thing, a blank canvas, a black void, a room with the lights turned off. But real nothing, the absence of space, time, matter, and structure, isn't like that. It's not dark, it's not empty, it's not anywhere, because where needs space to exist? So asking where the edge would be becomes a strange kind of question. It pushes against the limits of how we think. Some people imagine that if you traveled far enough, you'd find a kind of membrane, a border between space and not space. But what would hold it up? What would it be made of? What's beyond it? If it's a physical thing, then it exists within space, and that means it's not an edge, just another structure. If it isn't physical, then how would you even approach it? Others suggest the universe might just end the way a game map ends, a cliff into nothing, a sudden absence. But again, how would that work in real space? What would keep atoms from drifting past that point? What would stop light from continuing? Physics, as we understand it, doesn't support a sudden end like that. There's no reason for space to terminate at an invisible line. And so gradually, the question shifts from where would the edge be to does the concept even make sense? And from there to something more useful. What does space do? How does it behave? Where can signals reach? What's observable? What's testable? That's the edge we can talk about, the edge of the observable universe. The distance light has traveled since the Big Bang, given the expansion of space. That distance defines our current cosmic horizon, the largest sphere around us from which we've received information, about 46 billion light-years in every direction. That's not how far we can travel. It's how far light has traveled to us. Beyond that sphere, space continues almost certainly, but we can't see it. Not yet. Maybe not ever. That's a kind of edge, too. Not a physical barrier, just a limit on what we know, a soft boundary made of time and light, a border we didn't build but live inside. And it raises another question. If we can't reach the edge and we can't see past it, how do we know if space continues? Is it just an assumption? Is it based on patterns? The answer is both. It's an assumption supported by what we see. The universe looks uniform on large scales. There's no sign of approaching a boundary. The cosmic microwave background is smooth. Galaxies are distributed evenly. All of that suggests space doesn't just stop, but we can't prove it continues forever. We can only say it continues as far as we can see, and probably farther. For now, it's enough to say that the edge, if it exists, doesn't behave the way we expect edges to behave. It's not a place, not a barrier, not a transition. It's something more abstract, or maybe not there at all. Space expands, not like a balloon popping or a wave crashing or an object moving across the floor. Not suddenly, not violently, just steadily, quietly, relentlessly. The expansion of space isn't about motion through space. It's about space itself becoming more spacious. It's a stretching, not scattering. A change in the scale of the universe, not in the position of objects within a fixed container. This expansion began about 13.8 billion years ago. Not from a point in space, but from a state in which the universe was hot, dense, and as far as we can tell, nearly uniform everywhere. There was no center, no starting spot. The expansion happened everywhere at once. Every point in space began moving apart from every other point, and it hasn't stopped. It's easy to imagine that expansion is something that eventually runs out, like a rubber band that stretches and then relaxes, or a ball thrown upward that eventually slows and falls. But that's not how space behaves. Not by itself. Because the expansion of space isn't about momentum. It's about the dynamics of the fabric itself, shaped by mass, energy, and the rules of general relativity. And the strange thing is, over time, that expansion has not slowed down. It's sped up. That discovery came in the late 1990s. Astronomers studying distant supernovae noticed that those explosions appeared dimmer than expected, not just far away, farther away than they should be based on the known expansion rate. The only explanation that fit the data was that the rate of expansion had increased. The universe was stretching faster than before. That led to the idea of dark energy, a form of energy built into the vacuum of space itself. Not a gas, not a force, just a property, something that causes space to expand faster over time, not slower. It's not that galaxies are being pushed apart by some force between them. It's that the space between them stretches. And the more space there is, the more dark energy there is, and the more stretching occurs. It's self-reinforcing. More space means more expansion. More expansion means more space. This creates a universe where expansion never slows, where the distances between galaxies grow ever faster, where eventually most galaxies will drift so far apart that they vanish from view, not because they're hidden, but because their light will never reach us. The expansion will carry them beyond the cosmic event horizon. In that kind of universe, the expansion doesn't stop. It doesn't hit a balance point. It accelerates indefinitely. The scale of space continues to increase, even if locally, here in our galaxy and our cluster, things feel calm and stable. It's worth saying again, this expansion is not something you feel. Not on human scales. The Earth doesn't grow. The solar system doesn't drift apart. The Milky Way isn't stretching. Local gravity holds those things together. Expansion only wins on very large scales, where there's enough space between things for the effect to matter. But when it does matter, it dominates. Over billions of light-years space expands significantly. Over cosmic time, it changes everything. And it creates a universe where edge becomes meaningless. Because even if you tried to reach some distant location, to travel at the speed of light toward the furthest galaxy you can see, that galaxy would keep moving away. The space between you and it would continue to grow, and eventually that gap would widen faster than light can cross it. That's not breaking the rules of physics. It's not moving through space faster than light. It's the stretching of space itself. The coordinate grid gets larger. The ruler gets longer. And you can't run faster than the ruler can stretch. This has consequences. Galaxies that are currently visible to us, galaxies we can observe today, will one day disappear from view. Not by fading, but by slipping past the horizon. The light they emit from that point on will never reach us, ever. Not because we're not looking, but because there's no longer a path through space that leads from them to us. Eventually, only the galaxies gravitationally bound to our own, the local group, will remain visible. Everything else will drift out of range, carried by expansion into silence. Future astronomers, billions of years from now, may look into the sky and see only darkness beyond their cluster. No hint of the wider universe, no cosmic background glow, just isolation. That's not science fiction. That's physics. That's what happens when expansion doesn't stop. But it also means something else. that if the universe does have an edge, some final point beyond which space ceases to exist, we will never reach it. We'll never see it, not because it's far away, but because the path to it stretches faster than anything can travel. That's why cosmologists don't think in terms of reaching the edge. The edge, if it exists, is inaccessible, not just practically, but in principle. It lies outside the realm of what can ever be known, outside the causal structure of our universe. And that's assuming there is an edge at all. So when people say space is expanding, what they often imagine is an explosion, matter rushing outward into nothing. But the reality is quieter, stranger, more stable, but more permanent. Space expands because that's what it does. Because the energy built into its very structure causes it to grow, because on large scales that growth accelerates, because there's no counterforce large enough to slow it down. This expansion is not temporary. It's not something we're waiting to finish. It is the state of the universe, and it may be the permanent one. There's still debate. We don't know exactly what dark energy is or how it might evolve. It could change over time. It could fade. It could reverse. But based on what we see, that's not what's happening now. Right now, the expansion goes on. It carries galaxies away. It carries light away. It carries the edge of the observable universe ever outward. And it means that some parts of space, though real, are already lost to us. Not because we didn't look, but because we looked too late. So when we ask whether the universe has an edge, we also have to ask whether we'd ever notice one. Even if it did, would we recognize it? Would we see it approaching? Or would the expansion carry it away faster than we can ever reach? That's part of the mystery. The observable universe is not the whole universe. It's just the part we can see, the part from which light has had time to reach us since the beginning, a sphere centered on us. Not because we're special, but because that's how light works. Every observer everywhere lives at the center of their own observable universe. Each of those spheres stretches outward about 46 billion light-years in every direction, shaped by the time it takes light to travel, and the way space itself has expanded. But beyond that limit, beyond that shimmering edge of visibility, space doesn't stop. There's no sign that anything unusual happens at that boundary. No shift in structure, no change in laws, just distance, just delay, just the silence of light that hasn't had enough time. So what lies beyond? The first answer is simple, even if it's incomplete. More universe, more galaxies, more space, more time. There's no indication that the structure of the cosmos suddenly ends at our horizon. Everything we can see suggests that the patterns continue, the same density fluctuations, the same cosmic background radiation, the same spread of galaxies, uniform, smooth, flat. We assume that the universe goes on past what we can observe, because stopping at our current boundary would be arbitrary. There's no physical marker there, no edge in the equations, and no reason for the rest of space to be different, just because its light hasn't reached us yet. But assumption is not the same as proof. We don't know what lies beyond. We can't measure it. We can only infer. So our models, even the ones that say the universe is infinite, are still built on what's visible. And what's visible is a small part of the whole. If the universe is infinite, then the observable region is a tiny patch, a drop in an ocean of space. Not because it's small, but because infinity dwarfs anything you can measure. If you zoom out far enough, our entire cosmic horizon becomes a point, a speck in a sea of galaxies. But if the universe is finite, if it loops or folds or wraps, then it might be larger than the observable universe, but still limited in total size. In that case, we're still seeing just a portion, still missing the rest, still guessing. So the question isn't just what lies beyond the observable, it's how much is there beyond the observable? And even more deeply, can we ever know anything about it? In practice, probably not. There's no signal that travels faster than light, no telescope that can see through time, no shortcut through space. What lies beyond the observable horizon is causally disconnected from us. Not temporarily, not practically, fundamentally. That part of the universe exists outside our light cone. It cannot affect us. We cannot affect it. That sounds isolating, but it's true for every point in space. Every galaxy, every star, every planet sees its own slice of the universe. Some slices overlap. Others never will. That's how cosmic distance works. When space is expanding, you don't need an edge to be confined. You just need time. Now imagine this. There are galaxies whose light we will never see. Not because they don't exist, but because they're too far, moving away too fast. Even if we waited forever, their light wouldn't reach us. They're not hidden. They're unreachable. And if new galaxies formed out there tomorrow, if stars were born, if life emerged, if civilizations lit the skies with signals, none of that would ever reach us. Not because we're blind, but because we're late. That's the nature of cosmic isolation. It's not a failure of technology. It's a feature of space-time itself. Still, we can learn a little indirectly, by studying what we can see, by measuring the background radiation, by charting galaxies, by understanding how structure forms and how matter moves. All of that helps us infer the likely conditions in regions we'll never observe. And what we've learned is this. The universe beyond what we can see likely looks a lot like what we can see. Not identical, but consistent. Large-scale uniformity, smoothness, structure. That's the simplest interpretation of the data, and it's the basis for many of our models. But there's no law that says it has to be that way. The universe could be strange just beyond our view. It could bend, twist, break. It could end or change or fracture into other regions with other rules. We wouldn't know. We couldn't. And that's part of what makes this so difficult. We're used to thinking that anything real can eventually be seen, that everything has evidence, that enough time and study will reveal the truth. But the observable universe is a reminder that there are limits. Not just practical ones, but built-in ones. There are things we will never see, not because we haven't looked, but because they're outside of what seeing allows. Even so, we ask, we model, we wonder. Could there be other pockets of space beyond our own? Regions where conditions came out differently, where the laws of physics vary slightly, where even the number of dimensions is not the same. That's the idea behind some versions of the multiverse. Not just many universes in a poetic sense, but actual disconnected regions of space-time, each with their own properties, each expanding independently. If inflation happened the way some theories suggest, then such regions might exist. They might even be infinite in number, but we can't test that, not directly. Those other regions, if they exist, are permanently separated from us by space that expands too quickly to cross. They lie beyond the observable, not just in space, but in causality. So what lies beyond? Possibly everything, possibly nothing, possibly more of the same. What we know is this. Space doesn't end where we stop seeing. The edge of the observable universe is not the edge of the universe. It's just the limit of what light has told us. The cosmos continues. And in doing so, it reminds us of something quiet and strange, that our position, no matter how far we look, is always surrounded by more, not just in distance, but in mystery. In most things we encounter, there's a center, a midpoint, a location you can name as the origin. A room has a middle, a circle has a center, a city has a downtown, even a tree has a trunk from which branches spread. So when we hear that the universe began with the Big Bang, it's natural to picture an explosion in space, a burst from a point, with galaxies flying outward like sparks from a firework. And if there's an explosion, then there must be a center, a place where it happened. But that picture is wrong, not because it's too dramatic or too simple, but because it puts the universe inside something, a larger space, a bigger frame. The actual Big Bang wasn't an explosion in space. It was an expansion of space, a change not in the arrangement of matter but in the fabric that holds it. There's no center because space itself was created in that event. Not filled, created. The universe didn't expand into anything. It just expanded. Every point in space moved apart from every other point. Not because they were pushed, but because the space between them grew. And that growth happened everywhere, all at once. There was no origin spot, no special direction, just uniform expansion. The same rules applied across all regions and still do. That's why every observer, no matter where they are in the universe, sees themselves as being at the center of the expansion. From Earth, we see galaxies moving away from us in all directions. But from a distant galaxy, it looks the same. All other galaxies appear to recede from them. No location is privileged. The expansion looks the same from every vantage point. This is one of the stranger truths of cosmology, that every point in space is in a sense the center of its own observable universe. Not because we are each surrounded by space, but because we're each surrounded by the light from space, limited by time and distance. The illusion of a center comes from how we see, from how light arrives, from the fact that all our observations are made from a single location, here, Earth. Our instruments look outward. Our data comes in from all directions. And so naturally, we build maps with ourselves at the center. But those maps are just perspectives. They're not about where we are in the universe, only about where we are relative to the things we can see. If we were on another planet, in another galaxy billions of light years away, our maps would look the same. Still centered on us, still filled with galaxies retreating into distance, still shaped by time and light. So the center is a viewpoint, not a place. This isn't easy to internalize. Most of what we experience in daily life is based on fixed positions, up and down, left and right, near and far. A ball thrown from one side of the room to the other has a clear path. A clock ticks forward in one direction. Space has structure, time has flow. But on cosmic scales, those ideas break down. Direction becomes relative. Movement becomes expansion. Time becomes a coordinate, not a river. There's no up in space, no wall to push against, no axis to measure from. Just distance, and how that distance changes. So when we ask where the Big Bang happened or where the universe is centered, we're asking questions that don't apply. The Big Bang happened everywhere. It's not a point in space. It's a moment in time, a moment when space began to change. And because space itself has no edge, the idea of a center loses meaning. You can't measure from the middle if there's no boundary to measure toward. A loop has no start. A sphere has no special point on its surface. Every location is as central as any other. Even the idea of before the Big Bang may be meaningless, because time, like space, began in that moment. There wasn't a ticking clock that led up to it. Time is part of the universe, not something outside it. Of course, there are models that try to go further, that propose earlier states, cycles, bounces, collisions, but all of them work from the same principle, that our universe has no absolute center, that space is not expanding from a location, but within itself, that the structure is uniform, the same everywhere, and isotropic, the same in every direction. These aren't just guesses, they're supported by observations. The cosmic microwave background, for example, the faint afterglow of the early universe, looks nearly identical in all directions. No central hotspot, no directional bias, just a smooth pattern, gently rippled, evenly spread. That uniformity is part of what inflation theory explains. The idea that in its earliest moments, the universe expanded faster than the speed of light, smoothing out irregularities and stretching space so that everything looks the same no matter where you are. But that same smoothing also makes it harder to answer deeper questions. If everything looks the same, how do you know what lies beyond? If there's no center, how do you define shape? If the universe has no boundary, what gives it form? Those are questions of geometry and topology, of structure and connection. They don't rely on centers, they rely on relationships, how distances behave, how lines curve, how space joins back on itself or reaches out forever. And that's where our earlier questions return. Can space loop? Can it stretch infinitely? Can it end without ending? To answer them, we have to give up the need for a center. We have to stop imagining a place where it all began or a location we can point to and say this is the origin. Because in the largest picture there isn't one. There's only space and time and the rules that describe how they change. What's surprising, or maybe comforting, is that you don't need a center to feel grounded. You don't need to be at the middle of the universe to matter. Everything we observe is still real. Every measurement still counts. Every galaxy still moves. Every atom still follows the laws of physics. The center isn't where you are, it's just how you see. And when you let go of that idea, when you stop trying to find the central point, the rest of the picture becomes clearer. The expansion makes more sense. The shape of space opens up. The questions shift. Not where did the universe begin, but how. Not where does it end, but does it. Not where are we in relation to the whole, but what is the whole, and how does it behave? And that brings us to a different kind of question. If there's no center and no edge and space goes on in all directions, then what is infinity in this context? Not as an idea, not as a number, but as something you could move through, something you could fall into, not to reach the end, but simply to go on. When you hear the word infinity, it might feel distant, like a mathematical term, something abstract, an idea that belongs to equations and theorems, not to real things you can touch or move through. But in cosmology, infinity comes up constantly, not as a guess and not as decoration, but as a possible description of how space works. It shows up in equations and models, in how we think about distances and directions, and the number of things that might exist. It also raises a question that sounds simple, but isn't. If space is infinite, what does that really mean? Not in theory, not as a comparison, but in reality. Try to picture it. You stand still, and in every direction around you, space continues. Not for a while, not until a boundary, but always. No loops, no curves, no return path, just more space, stretching endlessly. That's not the only model of the universe. As we've seen, space might curve, it might fold, it might even loop. But based on current measurements, from cosmic background radiation, from galaxy clustering, from the distribution of matter on large scales, the geometry of the universe appears flat or so close to flat that any curvature is smaller than we can currently detect. And in a flat universe with the right topology, space could be infinite. No edge, no end, no total volume, just more space. If that's true, then the observable universe, the part we can see, is only a patch, a finite region inside an unbounded expanse. Our sphere of visibility doesn't mark a special zone. It's just the area lit up by light that's had time to reach us since the Big Bang. But beyond that sphere, the rest of space may go on without stopping, without repeating, without changing. And that's where the idea of falling into forever starts to matter. Because in an infinite universe, direction is unlimited. Distance is unlimited. Travel in principle is unlimited. You could pick a direction and move in a straight line forever. Not loop, not bounce, not come back, just continue. And no matter how far you go, there would always be more ahead, more galaxies, more voids, more structure. There would be no edge to reach, no sign that you're getting closer to anything final, just more. This doesn't mean you'd actually see infinity. Your vision would still be limited by light, by time, by the expansion of space. But the space itself, the coordinate grid, would stretch on endlessly. It also means that in an infinite universe, the number of galaxies is uncountable, not because they're too numerous to list, but because the total is unbounded. You could never write them all down, never map them all. There would always be more. Same for stars, same for planets, same for regions where conditions might be right for life. That's where things become even more unusual. Because in an infinite space with finite types of matter and finite ways particles can arrange themselves, certain patterns must repeat. Not necessarily in the same order or near each other or on scales we can imagine, but mathematically, the combinations of particles and energy are limited. Given enough distance, those combinations start to appear again, which means, at least in some models, there may be regions of the universe where matter is arranged just like here. Not close by, not in our observable sphere, but somewhere, some unimaginably far place where atoms line up the same way, a planet like this one, a solar system with similar dynamics, maybe even a person reading these same words. That's not science fiction. It's a consequence of applying statistical logic to an infinite space, a reminder that infinity isn't just a number, it's a structure. But we're not meant to think of this as clones or copies, not as destiny or magic, just as the result of unending variation. When the sample size grows without limit, even rare events become inevitable. Given forever, everything that can happen will. Yet none of those repetitions would be reachable, not in a practical sense, not even in a theoretical one. The distances between those regions would be far larger than the lifetime of the universe, far beyond what light could ever cross, even if given trillions of years. So they remain part of the model, not part of the map. Still, this version of forever, the kind that comes from flatness and expansion, helps shape how we see space, not as a bounded area, but as a direction, not as a thing with sides, but as a process that keeps going. And in that picture, you don't fall into infinity. You move through it. Any direction you choose, any distance you travel, leads only to more. No signposts, no special regions, no curvature to bring you back, just motion. Of course, gravity still matters. You can't actually drift forever in a straight line without encountering mass, galaxies, clusters, walls of matter strung across the cosmos. But the point remains. Space itself provides no limit. If you could go on, you'd never reach the end. In that sense, infinity is not a place. It's the absence of limit. And it's not just about size. It's about implication. Because if the universe is infinite, then many of our usual ways of thinking about total energy or average density or ultimate boundaries need adjusting. There is no total energy in an infinite universe. You can't sum it. There's no average that includes the whole. Only samples. No map that charts every region. No survey that completes the set. You're always inside a local view. No matter how far you see, there's more. You never arrive at the full picture. There's no border to step across, no edge to mark completion. That doesn't make the universe unknowable, just never fully known. And if you follow that thought long enough, something shifts. You stop asking how big the universe is. You stop asking what's at the edge. And you start asking how space behaves, how structure forms, how expansion changes. You begin thinking in terms of paths, not destinations, of rules, not limits. Because in infinity, rules matter more than boundaries. The way space curves, the way matter clumps, the way time unfolds, those are the things that shape what's possible, not how far you go. There's an idea that keeps coming back, even after you think you've set it down. A simple question with complex consequences. If you travel far enough in one direction through space, will you eventually return to where you started? It sounds like a question about walking a path, about covering enough distance, making no turns and looping back, like flying around a planet and landing where you took off without ever changing direction. But in cosmology, that question leads to deeper territory, because it's not really about the path. It's about the shape of space itself. When people ask whether the universe loops, they're asking about topology, not just how space curves locally, but how it connects globally. Whether it closes in on itself or goes on without limit, whether there's a repeating pattern behind the scenes, one we haven't yet noticed. We already know that space appears flat on large scales, that triangles drawn between galaxies behave the way standard geometry predicts, that light travels in straight lines unless bent by gravity. And if the universe is truly flat, then it might be infinite. But it also might be finite if the topology allows space to loop. The key distinction is between curvature and connection. A flat universe doesn't guarantee that space goes on forever. It just means that locally there's no bending. You can still take a flat surface and fold it, wrap it, stitch it together. Imagine a video game map where walking off one edge brings you back from the opposite side. That world feels infinite when you're inside it, even though it's not. Now imagine doing that in 3 dimensions, a space where the left edge connects to the right, the top to the bottom, the front to the back. There's no center, no outer shell, just repeating space, finite in volume, boundless in experience. That's a 3 torus, one example of a flat but finite universe. If our universe has that shape, then light could in theory travel around it. It could circle space and return to its origin, not by curving, but by moving straight through a space that folds back on itself. And if that happens, we might see repeated patterns in the sky. The same structures appearing in multiple places. The same patch of cosmic background radiation reflected more than once. Like hallways of mirrors that don't reveal the edges of a room, but give you overlapping views of the same scene. Scientists have looked for signs of that repetition. They've studied the cosmic microwave background, that faint glow from the early universe, for clues. If the universe loops on itself, that pattern of ancient light should show echoes. It should match up in specific ways in different parts of the sky. Circles that repeat, angles that align. So far, those signs haven't appeared. The data doesn't show the kind of repetition you'd expect from a small, closed topology. But that doesn't mean the universe doesn't loop. It might just mean that the loop, if it exists, is too large to detect. The repeated light hasn't had enough time to circle around. That's the strange part. If the loop is too wide, if the size of the whole universe is larger than the observable part, then the repeated images wouldn't be visible yet, or ever. The loop would exist but remain hidden, not because it's not real, but because light hasn't made the trip. So we're left in a place that's familiar by now, a space where the answer could be yes and yet unreachable, where a loop might exist but its evidence lies beyond the horizon. Still, the idea lingers. A universe that loops isn't just elegant. It's strange in ways that are hard to ignore. In a closed, finite space, you could travel in a straight line forever and never leave. The journey would never bring you to an edge. It would never bring you to new space, just a return after an unimaginable distance to where you started. But would you recognize it? In a universe that expands, the loop might take longer than the age of the universe to complete. By the time you returned, the place you began would have changed. Galaxies shift, stars die, light fades. Even the coordinates might stretch so far apart that what returns is unrecognizable. And then there's the matter of light itself. If photons travel around a looping universe, their paths would intersect. They'd crisscross the sky, creating patterns. The same beam of light might arrive from multiple directions. You could, in theory, see your own galaxy from behind, a mirror view from billions of years ago. It's not just a curiosity, it's a testable idea. And while current observations don't support that level of repetition, the data isn't perfect. We may yet find something subtle, a symmetry we missed, a hidden seam. But even if we don't, the possibility remains open. The loop may be there, too large to detect, too slow to reveal itself, like a wheel turning once every eternity. And if it does loop, what does that mean? It means the universe is finite in volume, but without boundaries. It means the edge we sometimes search for, the line we imagine at the outermost galaxy, doesn't exist. Because in a looping space, there is no outermost. There is no beyond. There is only more of the same. It also changes how we think about questions like total mass, total energy, total entropy. In an infinite universe, those values are undefined, always growing, never fixed. In a finite looping universe, they have limits, not because of constraints, but because of shape. That kind of universe feels more like a system, something whole, something contained not by a wall, but by geometry. It doesn't make the universe smaller, just different. But there's another version, too. A closed universe, not flat but curved. Not a torus, but a hypersphere. Still without edges, still finite, but with positive curvature, the kind that brings all paths back together eventually. like moving along the surface of a globe, only in more dimensions. That version has a different future. In some models it expands for a while, then slows, stops, then begins to contract, a long return journey to the state from which it started. The opposite of expansion, a collapse, a cosmic reversal. Right now, we don't see signs of that. The expansion isn't slowing, it's accelerating, and our best models point toward continued growth, not contraction. But the geometry still matters. The loop, if it exists, still tells us something, not just about where we are, but about how the whole fits together. And it raises a final question in this part of the path. If the universe doesn't loop, and it doesn't end, and it goes on forever, what surrounds it? It's a hard question to ignore, even if no one knows quite how to answer it. Maybe because it feels like it must have an answer. Even small children ask it. If the universe is everything, then what's outside it? What holds it? What surrounds it? We're used to things being contained. Rooms inside buildings, buildings on streets, streets inside cities. Everything seems to sit inside something else. So when we're told that space is expanding, that it's getting bigger all the time, it's natural to imagine it expanding into something, like a balloon inflating inside a room, a bubble growing inside a sea. But the universe isn't like that. It's not a thing expanding inside a larger space. It is the space. The balloon analogy helps sometimes, especially when we talk about curved, finite universes. But it has its limits, because it still relies on an outside. And in cosmology, there is no outside. Not in any direction. Not in any dimension we can meaningfully describe. Space doesn't sit within a container. It is the container. When it expands, it's not filling up an empty void. It's redefining what distance means within itself. So, if you were to ask, where is the universe? The answer isn't a coordinate. It isn't in a place. It's not located within a larger volume. It is the totality of locations. Even asking where is space expanding into is a misstep. It sounds right, but it sneaks in an assumption that there's a surrounding realm for it to grow into. But space doesn't expand into pre-existing space. It creates more of itself, more intervals, more separations, more distance. And that's where our thinking starts to stretch because we don't have much experience with this kind of thing. Everything we build has an edge. Every surface has a front and a back. Every room has walls. But the universe, if current understanding holds, has no outside. You can't step out of it. You can't fly beyond its bounds. You can't look down on it from above. Even if space is finite, even if it loops or closes, it's not sitting inside anything else. Just like the surface of a sphere doesn't need to be drawn inside a box. It defines its own completeness. Some theories do propose additional dimensions, higher spatial directions beyond the ones we experience. And in some models, our universe might be a kind of membrane, a brain, floating inside a higher dimensional space, like a sheet on a clothesline moving through a larger volume. In those models, there is something like an outside, but it's not space as we know it. It's not a place you could travel to. It's not accessible from within. It has different rules, different scales, maybe even different definitions of distance. And that's only if those models are correct, which right now is far from certain. They solve some problems in physics. They introduce others. But none have been confirmed. None make predictions we've yet been able to test. So the best answer we can give today is that there is no outside to the universe, not in the usual sense. Not a region, not a realm, not a background, just more universe or nothing at all. And when we say nothing, we don't mean a black vacuum. We don't mean emptiness. We mean the absence of any concept of space or time, a condition in which there is no where, no direction, no dimension, no possibility of moving or looking or measuring. That kind of nothing can't be traveled to. You can't reach it because it's not out there. It's not adjacent. It's not past the edge. It's what doesn't exist. This makes a lot of people uncomfortable. It's not satisfying to say there's nothing outside the universe. Not because it's untrue, but because it feels like dodging the question, as if we're just refusing to imagine something. But the truth is, the imagination needs structure to build from. If you take away all space and all time and all content and all direction, there's nothing left to place a thought into, nothing to even be outside of. No context, no frame. It's not that there's an invisible wall. It's that the whole idea of a wall doesn't apply. Even the word outside breaks down, because outside only has meaning when there's something to be outside of and somewhere to go. So what does this tell us? It tells us that the universe is self-contained, whether finite or infinite. It doesn't require a beyond. It isn't held by anything larger. It doesn't expand into the void. It simply expands. It defines its own boundaries, or lack of them. And if that's true, then every question about what lies outside the universe becomes a question about something that doesn't exist. Not because it's hidden, not because it's secret, but because it isn't there. That doesn't mean we stop asking. It just means we refine what we're asking. Instead of what's beyond everything, we ask, how did this structure begin? Instead of, where does it sit? We ask, how do its rules arise? Instead of searching for an edge, we try to understand the principles that make space and time emerge in the first place. And those questions, the origin questions, pull us further in, not out into some imagined beyond, but back toward the beginning, toward whatever condition existed before the expansion began, if there even was a before. Because if space and time had a starting point, then perhaps the idea of outside only makes sense after that point, not before. So what do we do with that? How do we even start to approach it? You don't have to understand all the answers to feel the shape of the question. You don't have to measure the universe to feel the distance. You don't have to solve for time to feel it passing. Right now, wherever you are, space surrounds you quietly, without edge, without center. You're sitting or lying or listening inside something vast, not separate from it, not outside it, inside. And even if it goes on forever, that forever includes you. It's easy to imagine the infinite as cold or unreachable, but it's not always like that. Sometimes it's small, local, tucked into ordinary things. The curve of a hand, the path of a thought, the number of moments between now and tomorrow. You've been holding infinity this whole time without needing to stretch. So now, if your eyes are heavy, or your mind is still, or your breath has slowed, you can rest. The universe won't end when you stop thinking about it. It will keep expanding or not. It will continue to surprise, to recede, to unfold. The questions will wait. And if you dream, and maybe you will, you might drift, not away from the stars, but deeper into them. Not toward the edge of something, but into the middle of everything. A place that doesn't need a border to feel complete. A quiet near the edge of infinity. We'll see you again whenever you're ready.